Hello there, and welcome to Earth Before Light, where curiosity moves at walking speed and science feels like a warm blanket rather than a chalkboard. Tonight, let's turn not upward to stars or outward to horizons, but downward, beneath soil and stone, into the quiet spaces our planet keeps to itself. Tonight, let's walk downward, past the cities, the roots of old forests, and the last glimmer of sunlight, into the slow, breathing darkness of the planet. We're looking for an ocean that doesn't move like waves or shine like moonlit water. It isn't a blue map line or a shipping lane. It's a hush, hidden inside minerals, tucked into the crystal lattices of rocks hundreds of miles below us. People sometimes call it Earth's hidden ocean, but it isn't a free sea you could sail. It's water bound as tiny molecules, hydrogen and oxygen woven into stone, lurking in a region geologists simply call the mantle. If that sounds impossible, it helps to remember that water is more than the puddles we step over. In the deep earth, certain minerals act like libraries, holding stories inside their structure. Under intense pressure and heat, minerals such as wadsleyite and ringwoodite can store surprising amounts of water as hydroxyl groups. Imagine a sponge, not wet on the outside, but with moisture locked into every fiber. Now shrink that image down to the scale of atoms and pack it into a layer of rock between roughly 410 and 660 kilometers down, the mantle transition zone. There, the planet keeps a secret. Enough water, by some estimates, to rival the oceans we know on the surface. Not a gleaming sea, but a reservoir that changes how our world works. Why would the Earth keep such a reservoir? Because the planet is not a solid statue. It circulates. Tectonic plates dive into the mantle at subduction zones, carrying seafloor sediments and hydrated minerals with them. That water doesn't vanish. It's traded, molecule by molecule, into the deep minerals that can hold it. Later, sometimes much later, heat and pressure will squeeze it back out, feeding magmas, sharpening earthquakes, softening rock, and even, in the longest of long arcs, finding its way to volcanoes and the sky. This hidden ocean doesn't make headlines because it refuses spectacle. There's no surf, no foam, no light. But it quietly edits the script of almost everything we see. It changes how easily rock flows, which changes how plates move. It alters how magma forms, which changes where volcanoes rise and what they release. It even influences the long heartbeat between wet climates and dry ones, because the deep water cycle and the shallow water cycle are parts of the same patient machine. As we settle into this story, think of the planet as a living archive of water, some singing in rivers, some sleeping in ice, some drifting as clouds, and some hidden far below, inside stones that never see the sun. Tonight, we'll read that deep chapter slowly. We'll listen for the faintest creak of plates, the distant whisper of minerals taking in and giving back what the oceans lend them. When you're ready, we'll open the next page and meet the transition zone itself, the twilight band, where rock becomes a reservoir and the planet learns to hold water in silence. Imagine opening a door where daylight thins but never truly ends. That's the mantle transition zone, the quiet band of Earth between about 410 and 660 kilometers down. Here, the same chemical ingredients wear different shapes. Under pressure so intense it squeezes atoms closer than neighbors in a crowded train. Minerals change their crystal architecture the way a story changes its ending. Most of the upper mantle is dominated by olivine, a green mineral at the surface that, down deep, is forced into new forms. At roughly 410 kilometers, olivine reshapes into wadsleyite. Denser, tighter, but with tiny structural hollows where hydrogen can slip in and rest. Deeper, near 520 kilometers, wadsleyite becomes ringwoodite, a still denser arrangement with its own small galleries for water to hide as hydroxyl. Then, at 60 kilometers, the lattice reconfigures again. Ringwoodite breaks into bridgemanite, a high-pressure silicate, plus ferropericlase. That last change, like a locked door, often drains the capacity to hold water. Below it, the lower mantle becomes a different kind of country. Seismologists discovered these boundaries first, not by sight, but by listening. Earthquakes send waves through the planet, and when those waves pass through a sudden change, 410, 520, 660, they speed up, slow down, or bounce. The echoes tell us there's a transition, and the crispness or blur of each echo hints at temperature, composition, even the presence of water. In places where the 410-kilometer boundary sits a little shallower and the 660 a little deeper, it's as if the whole zone has been swollen, warm, perhaps wetter. Where the boundaries crowd together, the zone seems compressed, cooler, perhaps drier. A map made of tremors, tracing a subterranean weather report. Why does this zone love water? It isn't thirsty in the way a dry sponge is, but its atomic rooms are shaped just right to host stray hydrogen. Hydroxyl threads into the lattice, changing how the rock behaves. A little water can soften it, lower the temperature where melting begins, and encourage magmas to form when slabs carry hydrous minerals downward. Think of the transition zone as a slow reservoir. Water goes in with the subducting plates, waits in mineral memory, and later, nudged by heat, pressure, and rising plumes, leaks back upward to feed volcanoes and eventually clouds. This is the hush beneath our oceans. Not a sea you could swim, but a capacity, measured in percent or parts per million, that quietly steers the rhythms of plates, magmas, and climates. In the next chapter, we'll follow a single raindrop's long pilgrimage, from sky to river to trench to crystal, and hear how it learns to speak the language of stone. Begin with a cloud. Sunlight lifts seawater into the sky, and the air cools it into pearls. One pearl falls. Your raindrop lands on a mountain, slips into a mossy stream, and rides a river to the sea. Nothing unusual until it meets stone that will become a ship. Out on the ocean floor, Basalt quietly grows at mid-ocean ridges. Cold water seeps into cracks and reacts with hot rock, locking hydrogen and oxygen into new minerals, serpentine, amphibole, clays. Your raindrop changes citizenship. No longer free, it's folded into crystal, the way a note is folded into an envelope and filed. Time passes in tectonic years. The ocean plate cools, thickens, and finally bows downward into a trench. Subduction is not a plunge but a slow kneel. As pressure rises and temperatures climb, those hydrous minerals begin to let go. They dehydrate, releasing water into the overlying mantle wedge. And water, quiet as it seems, has a powerful voice down here. It lowers the solidus, the temperature at which rock starts to melt. Patches of mantle begin to drip into magma. This is how arcs of volcanoes are written along the edges of oceans, not by fiery aggression, but by small gifts of water from a sinking plate. Magma rises, cools, crystallizes. Some gas escapes to the sky. Some magma builds new crust. Some freezes below ground as granite, where it will wait for a future mountain to carve it free. But not all water turns around so quickly. Some rides the slab deeper, passing the first heat where amphiboles break, past the depths where serpentinite unravels. At 410 kilometers, your raindrop meets a new host. Wadsleyite opens its tiny rooms. Hydrogen threads in. A little deeper, ringwoodite takes over, holding even more. The molecule is now part of the mantle's memory, stored in the transition zone like a page pressed inside a book. How long will it stay? That depends on the planet's slow weather, on mantle plumes rising like warm sighs from deeper down, on slabs that stall and pool, on continents that tear and drift. When a plume stirs the transition zone, some of that stored water leaks upward again, priming hotspots, feeding magmas that punch through old roofs of rock. The sky receives another whisper of vapor. Somewhere, centuries later, a cloud grows heavy, and a raindrop begins. A cycle, then, but not a circle drawn in a day. It's a spiral that threads sky to stone, trench to volcano, mineral to cloud. The hidden ocean is not a place. It's a promise the planet keeps. What goes down in time helps lift something up. A story this deep needs evidence, signals that travel from darkness to daylight without losing their meaning. The planet sends those signals in two languages, waves and stones. First, the waves. When an earthquake rings the earth, its vibrations speed through rock like music through wood. At 4 and again near 660, those waves stumble, split, or hurry, proof that minerals have changed shape. In some regions, the notes bend more than elsewhere, as if something has softened the instrument. Laboratory experiments show that a whisper of water, hidden as hydroxyl inside wadsleyite and ringwoodite, can do exactly that. Lower rigidity, tweak velocities, nudge the boundaries up or down. Seismologists make maps from these tiny hesitations, and the maps suggest patches of the transition zone that are wetter, more accommodating than their neighbors. Then, the stones. Diamonds are couriers from the deep, rising in rare, violent eruptions and arriving at the surface still holding what they swallowed below. In one such diamond, scientists found a fleck of ringwoodite, the high-pressure form of olivine that lives in the transition zone. Trapped inside that fleck was water, not as droplets, but as part of the crystal's very pattern. It was a postcard from 500 kilometers down, stamped with the simple message, "We can hold more water than you think." There are other clues. Some stretches of the mantle conduct electricity better than others. Water helps carry charge. Melt seems to appear where slabs stall in the transition zone. Water lowers the melting point. In volcanic chains far from subduction zones, Hawaii, Iceland, chemical fingerprints hint that the source mantle carried ancient recycled seawater, stored and then released after a long sleep. Together, these lines converge: seismic kinks, electric whispers, laboratory crystals, and the rare diamond that crossed a pressure frontier with its secret intact. None alone would convince. But like stars that only form a constellation when you step back, the pieces arrange themselves into a picture. A planet that stores water and mineral memory between 410 and 660 kilometers deep, and trades that water invisibly, patiently, with the world we breathe. Proof, though, is never a finish line. It's an invitation. Each new measurement suggests a question. How patchy is this reservoir? How quickly does it turn over? Does it grease the skids for plumes or break them? Does it slow earthquakes or sharpen them? The answers will come in better wave maps, more precise lab experiments, and the luck of another diamond bearing a blue-gray shard of ringwoodite from the silent zone below. For now, it's enough to know that the hidden ocean is not myth but mechanism, a quiet capacity that changes how stone flows, how magma forms, and how the surface breathes through ages. In the next part, let's step into a subduction zone and watch, in slow motion, how a sinking plate wrings water from rock and feeds fire above it. Picture a dark coastline without a map, an oceanic plate gliding inland, then bending, then sinking, the slowest bow you can imagine. Subduction is patience made into geology. The plate that once grew at a mid-ocean ridge carries souvenirs from the surface. Cracks healed with minerals that drank seawater, veins of serpentine and amphibole, thin films of clay that hold tiny ghosts of rain. As the slab descends, pressure gathers and temperature rises. Hydrous minerals are guardians only up to a point. One by one they unfasten. First the more delicate clays and amphiboles, later the tougher serpentines and lawsonite. Each release a quiet exhale of water into the mantle wedge above. Down here, that exhale is powerful. Water lowers the temperature at which rock begins to melt. What was solid starts to blur at the edges. Little pockets of melt appear, then merge, then begin their slow ascent. buoyed by the simple fact that melt is a little lighter than the rock that birthed it. At the surface, we see the consequence as volcanic arcs tracing the rim of oceans, volcanoes singing a song water wrote in the dark. Their magmas are often richer in volatiles, their eruptions sometimes more explosive. Their plumes a reminder that the sky and the mantle are not strangers. Between trench and arc, the forearc can be strangely cool, sometimes infiltrated by fluids that make rocks slippery, sometimes hosting slow, shivering motions, tremor, slow slip, that feel like a planet trying not to wake you as it turns over in bed. Not all water takes the exit ramp into volcanoes. Some remains loyal to the journey, traveling with the slab into greater depths, finding new hosts as crystal structures change. In the transition zone's twilight, ringwoodite and wadsleyite open their small interior rooms. Hydrogen threads in again. Here the hidden ocean keeps its ledger. Deposits arrive from above. Withdrawals leave with rising plumes. The balance is never perfect, but it is steady enough to shape continents, climates, and the long breath of the carbon cycle. Stand on a beach some night and listen to a quiet wave break. The hiss you hear lasts a heartbeat. The hiss of water released from a sinking plate can last millions of years, and its echo is a mountain chain, an ash cloud, a new piece of crust cooling in the rain. If rock could dream, it would dream slowly. It would flow the way mountains sigh, the way glaciers forget and remember their path. Down in the mantle, flow is not a river. It's the patient rearrangement of atoms, the steady glide of crystals past one another. And water, hid in the lattice as tiny hydroxyls, touches that process with soft hands. Add a whisper of water to olivine, and the crystals become kinder to motion. Boundaries between grains loosen. Defects slip more easily. Scientists give this many names: creep, diffusion, dislocation, but the feeling is simple. A small dose of water lowers the resistance, like oil in a hinge that's been stiff for a century. The rock doesn't melt. It only becomes willing. This willingness matters where the planet draws an invisible line between hard and soft, the lithosphere above and the asthenosphere below. The lithosphere is the rigid raft that carries continents and seafloor. The asthenosphere is the supportive pillow that lets those rafts glide. A touch of water helps keep that pillow supple, so plates can drift, meet, and part, without the world splintering more than it must. Where the asthenosphere is slightly wetter, plates may move more gracefully. Where it is drier, the dance can grow jerky, stress building like a breath held too long. Water also tilts the balance toward melting. It lowers the temperature at which rock begins to generate a little magma, the first bright beads in an otherwise dark fabric. That's why places fed by water, whether above subduction zones or where deep plumes meet stored moisture in the transition zone, are more likely to raise volcanoes. The chemistry of those lavas remembers the presence of water. More gas, different minerals, a voice that crackles in the sky. Even earthquakes feel the touch. Along faults, fluids can slip into tiny spaces, changing pressure, reducing friction, turning a potential snap into a slow shiver. In subduction zones, patches that breathe water in and out may host tremor and slow slip, events too gentle to topple a cup, yet large enough to redraw stress maps deep underground. The hidden ocean doesn't shout. It edits. It trims the sharp edges of motion and sometimes, quietly, sharpens them elsewhere. If you could place a stethoscope on the planet, you might hear the difference between wet and dry stone. One a little more yielding, one a little more stern. Neither is better. Both are parts of a single instrument. But imagine the length of concert we're attending. A symphony measured in millions of years. The score inked in hydrogen and oxygen that learned to live inside crystal. Up here, a glass of water is simple. Down there, a trace of water is strategy. It shapes how heat escapes, how continents wander, how mountains rise and weather into sand, and how the sea reclaims that sand again. The soft hands of water hold no steering wheel, yet the road keeps curving to their touch. Far below the floors of oceans, deeper than memory can picture, warm columns of rock begin to rise. We call them plumes, not flames, not rivers, but slow, buoyant threads of mantle that drift upward for thousands of kilometers. They move at the pace of continents dreaming, carrying heat from the deep toward the cool lid of the earth. On their way, some of these plumes enter the twilight of the transition zone, the layer that can store water inside minerals like a library stores whispers. Here the plume meets a choice. It can pass as a stranger, or it can pause and sip. The rock around it, wadsleyite, ringwoodite, holds hydrogen in tiny rooms, a little warmth, a gentle change in pressure, and those rooms open. Water leaves mineral memory and joins the rising flow, not as liquid, but as a quiet influence that lowers the melting point and softens the path ahead. When the plume reaches the boundary at 660 kilometers, the crystal architecture changes again. Some plumes stall there for a time, like a traveler catching breath at a mountain pass. Others push through. Either way, water helps. It encourages the first bright beads of melt to appear, which in turn makes the plume more buoyant, more eager to continue upward. The melt gathers, coalesces, and begins its long ascent toward a place we can finally see. A hot spot at the surface, a shield volcano rising layer by patient layer, lava looking like dark honey under the moon. In islands strung like rosary beads across the sea, you can read the plume's diary. Each island is an entry, born from melt that carries a faint signature of old seawater, recycled and stored below, then released after ages of quiet keeping. The chemistry is not a shout, only a nudge, ratios and traces that say softly, I have been down there. Night after night, the ocean breathes and the volcano breathes with it. A conversation between sky and stone that never needs words. Plumes do more than build islands. They stitch heat into the base of continents, weaken old scars in the crust, and sometimes, in rare and overwhelming chapters of Earth's past, flood the surface with broad fields of lava that change climate and life. Even in those grand gestures, the hidden ocean has a hand on the brush. Water helps decide how much melts, how fast, and how the gases escape into the air we share. Picture a lantern moving through fog. The fog is the transition zone. The lantern is the plume. Where they cross, the light grows a little brighter, the path a little clearer, and a distant island begins to exist in the future tense. In the next part, we'll leave the deep updraft and visit the opposite motion. Slabs that sink and sometimes stall, where water, rock, and gravity negotiate how far down a piece of ocean can go. Not every journey downward is a straight fall. Some oceanic plates, after thousands of kilometers of steady descent, reach the transition zone and hesitate, as if the Earth itself were asking them to pause and think. At 660 kilometers, the mineral architecture changes, and with it, buoyancy and strength. The slab meets a stiffer country. Some parts punch through into the lower mantle. Others spread out like a tired traveler laying a coat on the floor, flattening, stalling, and lingering in the twilight. Water helps decide which path a slab takes. As hydrous minerals break down along the way, water escapes, softening the surrounding mantle and priming it for melting above. But deeper in, pockets of the slab can stay colder than their surroundings. In those chill cores, the crystal structure of olivine may remain, not yet transformed, holding on to a fragile state the way ice clings to shade at noon. That mismatch, cold against warm, old structure against new, can set the stage for deep earthquakes, events that tap and shiver hundreds of kilometers below us. We don't feel most of them on the surface, but the planet does. Their waves carry messages about temperature, composition, and water. When a slab stalls, the transition zone becomes a waiting room. Water once carried down is exchanged into wadsleyite and ringwoodite, swelling the zone's capacity like a sponge, quietly taking on weight. Later, a rising plume may pass through and reclaim some of that stored moisture, using it to coax the first bright beads of melt from the shadowed rock. In this way, distant parts of the mantle talk to each other. A sinking plate leaves a letter. A plume, decades or millions of years later, reads it. Even where slabs do push through the 660-kilometer gate, water leaves fingerprints, helping govern how the plate bends, how it breaks, and how the boundary itself warps across the globe. In places, that boundary sags like a hammock under extra load. Elsewhere, it arches, taut and high. Seismic maps sketch these shapes like contour lines on a secret atlas. Stand for a moment, on a quiet night coast, and picture the ocean under moonlight. Surface waves arriving, then sliding back. The deep earth moves on a longer tide. Plates descend, pause, and sometimes return their gifts to the world above. The hidden ocean is the tidekeeper, measuring these exchanges in whispers of hydrogen bound to stone. Counting a hidden ocean is like weighing a lullaby. You can't scoop it. You can only listen for what it changes. So scientists begin with capacity, the question of how much water the minerals could hold if every small room in their crystal lattice were occupied. In the mantle's transition zone, wadsleyite and ringwoodite are generous hosts. Under the pressures and temperatures there, laboratory crystals accept water, really hydrogen bonded as hydroxyl, on the order of percent by weight for wadsleyite, and around 1% or so for ringwoodite. Those sound like small numbers, but spread across a shell of rock hundreds of kilometers thick, the capacity adds up. If those minerals were fully saturated everywhere, the transition zone alone could store an amount of water comparable to at least one of our surface oceans. But capacity is not content. The real Earth is patchy, busy, and patient. Some regions are wetter, where slabs have delivered more hydrous minerals, or where the zone has swelled warm and welcoming. Others are drier, where circulation has whisked water away, or where colder slabs have not yet traded their cargo to the host minerals. Seismic maps, conductivity hints, and the rare ringwoodite-bearing diamond tell the same gentle truth. There is water in the zone, but it does not fill every room. And beyond the transition zone, the numbers change again. Above it, the upper mantle holds less on average. Different minerals, fewer places for hydrogen to rest. Below it, the lower mantle's dominant phases are less accommodating. The lattice rearranges into structures that prefer to travel light. So the hidden ocean has a favorite depth, a twilight band where the planet is best at remembering water. What would it mean, emotionally, if the tally leaned high or low? A wetter transition zone encourages melt in the right circumstances, softens rock so plates move with fewer jolts, and primes plumes to build islands more readily when they pass through. A drier one resists, slows, and saves its whispers for later. Either way, the surface feels the difference in long, slow beats, volcano chains growing a bit faster or slower, continents drifting with a touch more grace or grit, climates breathing on timescales far beyond a human life. So we hold two ideas at once. The transition zone could store an ocean's worth of water, and the Earth likely keeps only a fraction of that there at any moment. Enough to matter. Enough to guide the choreography of stone. It is a reservoir not defined by shorelines, but by possibility. Rooms that can be occupied, emptied, and occupied again as plates dive, plumes rise, and the deep cycle turns. If you listen closely, you can almost hear the arithmetic the planet is doing, quiet additions and subtractions, written in hydrogen and oxygen, balanced over millions of years. Think of Earth breathing with two chests. The first is the one we know. Clouds gathering, rain falling, rivers running, oceans swelling and shrinking with wind and season. That's the shallow cycle, the quick pulse that waters forests, turns turbines, and writes weather across our windows. The second chest rises and falls so slowly you could sleep a lifetime and never notice. That is the deep water cycle, the quiet commerce between ocean, rock, and mantle, measured not in days but in ages. On the surface, water moves freely. It evaporates, condenses, freezes, melts, and flows downhill, always seeking the sea. In the deep, water mostly travels as a rumor inside minerals. Oceanic plates take it down, first by soaking at mid-ocean ridges and seafloor cracks, then by binding into hydrous minerals that ride the slab into the planet. The shallow cycle sends water to the trench as rain. The deep cycle receives it through stone. The exchange is never one way. As slabs kneel into the mantle, their minerals unfasten. Water is released upward into the mantle wedge, helping rock to melt. Magma rises. Volcanoes breathe. With every eruption, a little of the deep cycle becomes sky again. Steam drifting into clouds, ash feeding soils that will carry streams. Even where volcanoes never break the surface, where magmas stall and crystallize underground, the volatiles they shed can migrate and mingle, joining the longer conversation that eventually returns moisture to the air. Timescales divide these rivers. A storm crosses a valley overnight. A plate crosses an ocean in tens of millions of years. Yet the two cycles are coupled. If the deep cycle primes more melting beneath an arc, it can shift how much gas escapes to the atmosphere over geologic time. If climate nudges sea level and erosion, it can change how quickly sediments and the water they hold are delivered to trenches. The breath of the sky and the breath of the mantle do not match, but they rhyme. This perspective softens the border between above and below. A snowflake landing on a cedar branch may someday enter the mantle as part of a clay mineral. A whisper of hydroxyl bound into ringwoodite may, one era later, return as mist over a sleeping lake. The hidden ocean is not a separate sea. It is the planet's long memory of water, keeping accounts while the surface writes poems. If you listen closely tonight, you might hear both chests rise and fall, the quick sigh of weather and the slow, patient inhale of stone. Some messages arrive folded into paper, others arrive folded into light. This one came folded into carbon, lifted from the deep by an eruption so fast it outran time. Kimberlite pipes are the planet's sudden elevators. In a few hours, they carry passengers that have waited for eons, diamonds, still cool from the pressure where they formed, still clutching tiny fragments of the world they knew below. Inside one such diamond, scientists found a speck, not a gem within a gem, but a mineral inclusion, sealed so early and so tightly that it kept the conditions of its birth. Under the microscope, that fleck revealed itself as ringwoodite, the high-pressure form of olivine that belongs to the mantle's transition zone. And within its crystal, woven into the lattice, not pooled as droplets, was water. Not much by volume, but unmistakable in spirit. Hydrogen and oxygen bound into the structure like a secret tattoo. Why did this matter? Because it was a postcard from 500,000 kilometers down that no one could misread. Seismic waves had already sketched the outlines of a wet transition zone. Lab experiments had shown that ringwoodite could host significant water. Electrical conductivity hints and volcanic chemistry had joined the chorus. But this diamond was different. It was a physical fragment of the twilight layer itself, proof that minerals there do, in fact, carry water as part of their being. Think about the journey. Long before the diamond rose, a plate had drifted, soaked, and sunk, delivering water into the mantle. Wadsleyite and ringwoodite took it in, room by room, into their atomic architecture. In some small corner of that vast zone, carbon crystallized into diamond, trapping a grain of ringwoodite with its quiet cargo. Ages later, a kimberlite eruption surged upward like a pressure-driven breath, delivering the diamond to a place where human hands could open its story. Hold that image gently. An ancient raindrop, changed beyond recognition, traveling as part of a crystal, sleeping in stone, then riding a volcanic elevator to the air. The planet does not waste water. It teaches it new languages. In the deep, water speaks as hydroxyl, as a shift in seismic velocity, as a lower melting point, as a softened flow. In the sky, water speaks as cloud and weather. In the diamond, it speaks as proof, spare, elegant, undeniable. We will meet other messengers in this tale. Basalts with a hint of recycled ocean, slabs that breathe fluids as they kneel, plumes that grow more buoyant when they sip the zone's stored moisture. But the diamond is a favorite because it is small enough to hold, and yet it carries an ocean's idea. Some truths don't travel by light or sound. They travel by current. When distant lightning flickers, when the sun stirs Earth's magnetic field, faint electrical tides flow through the planet. Rocks are not perfect insulators. They answer those outside signals with a response of their own, and from that response we learn what they are holding. This is the quiet craft of magnetotellurics, listening to natural electromagnetic waves and measuring how easily the subsurface conducts electricity. Dry, tight crystals tend to be reluctant. Add a little melt or a trace of water bound inside minerals, and the reluctance softens. Protons find pathways. Defects align. The stone, still solid, becomes a more willing host for charge. Across the world, maps drawn from these measurements show patches of higher conductivity near the mantle's transition zone, soft blue rooms in an otherwise stone-built house. They do not prove a lake. They suggest a capacity. Minerals like wadsleyite and ringwoodite with hydrogen threaded into their lattices, or small films of melt coaxed into existence because water lowers the temperature at which rock begins to liquefy. Either way, the hidden ocean leaves an electrical accent on the score. There's a poetry to this method. We ask the sky a question about the deep earth, and the sky answers by humming. The hum passes through mountain roots and ocean basins, through slabs that kneel and plumes that rise, and returns to our instruments as numbers, tiny, precise, patient. We invert those numbers into images, silhouettes of wetter corridors, drier buttresses, places where the 410 and 660-kilometer boundaries seem swollen, as if warm and accommodating, and places where they tighten like a belt. In labs, under anvils that squeeze harder than any hand, and heaters that glow like small suns, crystals taught us why. A sprinkle of water changes how electrons and protons move, how defects hop, how easy it is for a rock to carry charge without melting into a wire. The deep earth uses these rules to speak to us across impossible distance. We only had to learn its dialect. Electrical whispers don't travel alone. They join seismic echoes, diamond postcards, and the chemistry of lavas in a choir that says, gently but firmly, there is water down there. Not in pools, but in patterns, written into structure, borrowed by melts, traded in and out as plates and plumes pass slow messages hand to hand. Imagine standing in a night field and feeling, more than hearing, the buzz of distant power lines. Now move that sensation inward, beneath continents and seas, until the feeling maps a sea of possibility between 410 and 660 kilometers deep. That is what these measurements give us. Not a photograph of water, but its fingerprint, pressed lightly into stone. In the next part, we'll follow another thread of evidence. Earthquakes so deep they should be impossible, and what their existence tells us about cold slabs, stubborn minerals, and the hushed presence of water. Close your eyes and imagine a hand squeezing warm wax. It deforms quietly. It doesn't snap. Deep inside Earth, rock should act like that. Too hot, too pressurized to break with a sudden crack. And yet, between 300 and nearly 700 kilometers down, earthquakes do happen. They arrive as crisp, high-frequency whispers on our instruments, traveling up from a darkness where brittle failure should be impossible. Why follow a sinking plate into that dark? It is colder than the mantle it enters, a ribbon of winter laid into a summer sea. In its chilled core, the mineral olivine can persist past its comfort zone, refusing to transform into the denser shapes, wadsleyite, then ringwoodite, that the pressure prefers. This stubborn pocket is called a metastable wedge, and inside it, change builds like weather. One explanation is transformational faulting. When olivine finally yields to the new structure, the phase change can advance in a runaway front, releasing strain like a held breath. Picture a sheet of frost suddenly turning to rain within the rock. Volumes shrink a little, stresses jump, and a rupture races through the zone. Another explanation leans on microscopic anti-cracks, tiny compaction features that align and link, letting a failure propagate even where ordinary cracks cannot open. Both are ways for stone to break the rules without breaking itself apart into gravel. Where does water fit in a quake so deep? Not as free fluid flooding a fault, but as influence. A trace of water in the lattice can speed or slow the transformations, grease the motion of defects, and weaken grain boundaries. Subtle changes that tip the balance toward instability. Earlier in the descent, Dehydration of hydrous minerals can trigger shallower tremors by releasing actual fluids. Deeper down, the water is mostly captive, but it still edits the script through mineral physics. Even a whisper of hydroxyl can decide how easily atoms rearrange, how fast a phase boundary runs, and how likely a rupture is to grow large enough to sing to the surface. Seismologists read these events like letters. A deep quake's depth, frequency, and aftershock habits sketch the temperature of the slab, the shape of its metastable core, and the presence or absence of that quiet, bonded water. Each shock is a reminder that the hidden ocean speaks not only through volcanoes and conductivity, but through impossible-seeming earthquakes that map the twilight where minerals change their minds. Some nights the planet turns over and sighs. Sometimes, even in its sleep, it startles. That startle is what our seismometers feel from half a world away. Every journey has a threshold where the air changes, where the sound of your footsteps becomes different. For Earth's interior, that threshold is the boundary near 660 kilometers depth, the place where one mineral architecture gives way to another, and the planet quietly rearranges its furniture. Above 660, in the transition zone, olivine has already been pressed into denser forms, first wadsleyite, then ringwoodite, each with small interior rooms where hydrogen can rest as hydroxyl. That's why this twilight layer can hold so much remembered water. But at 660, the blueprint shifts again. Ringwoodite breaks down into two new residents. Bridgmanite, a high-pressure silicate, and ferropericlase, an iron-magnesium oxide. The house is still stone, but its rooms are a different shape, and the space for water grows scarcer. This change is more than a mineral name tag. It's a change in buoyancy, strength, and the way heat and motion travel. A sinking slab arrives at the gate carrying cold and history. If it remains dense enough, it punches through, threading into the lower mantle like a ribbon. If not, it may flatten and stall, spreading out along the boundary, letting the transition zone sip more water from its minerals while it waits. In some places, the gate itself sags under the weight. In others, warmth below makes it arch upward. Seismic waves trace these deformations like fingers reading braille. For water, the gate feels like a customs check. Above it, the transition zone can store generous amounts in ringwoodite's lattice. Below it, bridgmanite and ferropericlase are stricter hosts. Much of the hydrogen that once found a bed must now travel differently, partitioning into small amounts of melt where conditions allow, hitching rides on minor phases, or waiting in the last pockets of ringwoodite that survive in colder patches. The result is a natural segregation, a wetter twilight above, a drier deep below, and yet, nothing here is absolute. Plumes rising from the lower mantle can push through the gate, warming and softening it, coaxing a little stored moisture from the rocks just above. Slabs that penetrate can ferry traces of water deeper than usual, writing faint signatures into places that prefer to travel light. On geologic timescales, this negotiation shapes how the mantle mixes, sometimes layered like a cake, sometimes stirred like a slow soup. If you listen for feeling rather than data, the 660-kilometer boundary is a heartbeat valve. With each long beat of convection, material passes one way or the other, pressure resets, and the planet's deep circulation continues. The hidden ocean pools above the valve, then leaks, then pools again. Never a flood, always an influence. Stand at the shoreline some night and imagine a tide you can't see. Just the knowledge that water is coming or going, reshaping the edge of things by patience alone. That is the tide at 660. Mineral rooms closing and opening, stones learning new ways to hold or release the oldest molecule to touch our lips. When rock remembers water, the sky eventually finds out. Volcanoes are the translators. They take the language of hydroxyl hidden in minerals, mix it with heat and time, and speak it back to the air as steam. Not all volcanoes tell the same story. Along subduction zones, the tale begins with a sinking plate that releases water into the mantle wedge. That water lowers the melting point, so magmas form more easily. Those magmas rise carrying dissolved gases, H2O, CO2, a trace of SO2, like notes tucked into their pockets. Near the surface, pressure falls. The gases undissolve, expand, and push. Sometimes the push is gentle, pillows of vapor drifting into cold night. Sometimes it's insistent, turning a quiet conduit into a crowded stairwell where ash and pumice rush upward in a hurry. Either way, every plume is a letter addressed to the sky. We remember the sea. Hotspot volcanoes, Hawaii, Iceland, speak more slowly, like storytellers by a hearth. Their magmas begin in mantle plumes that rise from deep, perhaps sipping moisture stored in the transition zone. The lavas there are often runnier, spreading out as shields, their steam a steady breath rather than a shout. Chemistry gives them a faint accent, a hint that some of their water was recycled long ago and then kept safe in mineral memory until heat asked for it back. Listen for the emotional truth beneath the petrology. A planet that exhales water through fire is not wasteful, it's cyclical. What goes down as rain rides stone for ages, and returns as cloud is part of one continuous breath. Volcanic steam seeds weather, moistens high air, and in time falls again on cedar needles and river stones. The deep and the shallow cycles clasp hands at a crater rim, even when magma stalls beneath our feet, cooling into granite instead of erupting. The gases it releases can migrate through cracks, changing the chemistry of groundwater, feeding hot springs that hiss softly in winter. That too is an exhale, filtered through rock. It's tempting to count only the dramatic pages, fountains, curtains of fire, thunder in the dark. But most of Earth's degassing is patient and small, a continuous whisper rather than a single chorus. Add the whispers together, and you get climate's background choir. Long-term water and carbon budgets adjusted grain by grain, breath by breath. On some evening, far from any volcano, step outside after rain. Smell the air, wet stone, leaf, a mineral sweetness. Part of that scent began in darkness, bound to lattice, stored where light never reaches. Tonight it returned, and the planet felt lighter. Weather speaks in hours. Climate speaks in centuries. The deep earth speaks in ages. Yet all three share the same water. On the surface, storms shuffle moisture from sea to sky and back again. Far below, the mantle keeps a ledger, accepting rain hidden in minerals, returning steam through fire, and quietly shaping the background rhythm against which ice ages and monsoons perform. Think of two gears, one small, spinning fast, and one large, turning almost too slowly to see. The shallow water cycle is the small gear. Evaporation, clouds, rivers, glaciers. The deep water cycle is the large gear. Subduction, storage in the transition zone, and degassing through volcanoes and mid-ocean ridges. When the large gear moves, even a little, the small gear feels it. More water returned through volcanism can, over geologic time, tilt humidity patterns and feed the long arc of the carbon-silicate cycle. Rain weathers fresh rock. Rivers carry ions to the sea. Organisms lock carbon into shells. Plates deliver that carbon, and its companion water down again. Degassing brings both back. A breath out, a breath in, spaced by millions of years. Water is a master of leverage. In the mantle, a trace lowers the temperature where rock begins to melt, deciding how much magma is made, how much gas escapes, and where volcanoes rise. At the surface, that choice changes how much fresh basalt is exposed to rain, how hungry landscapes are for carbon, and how strongly the planet's thermostat can pull itself back from extremes. No single eruption rights the climate, but the sum of many small exhales helps set the stage on which ice sheets grow and retreat. There is humility in this picture. We're tuned to the quick, a season of drought, a storm out of place, a scorching summer. The deep cycle answers in chapters so long we measure them with fossils and seafloor stripes. Still, knowing it is there changes how the present feels. Tonight's rain has a lineage. Somewhere under an ocean arc, steam is rising that began as snowfall before there were cities. Somewhere in the transition zone, hydroxyl waits in ringwoodite, a deferred cloud for a future sky. If climate is the long poem of water and carbon, the hidden ocean is the quiet rhyme scheme that holds the verses together. Not visible, not loud, just insistently present, guiding the meter of a planet learning to keep itself in balance. Where continents drift apart, the planet opens a soft seam and breathes. Mid-ocean ridges are not mountains that rose. They are wounds that never quite close, stitched by lava that arrives warm and quiet from below. Here, at the world's longest chain of volcanoes, the deep cycle exhales in a steady whisper. New crust forms as basalt pours out and chills into pillows. While it cools, seawater slips into fractures and pores, drawn by heat like breath toward a candle. Down it goes, trading temperature with the rock, picking up metals, learning the taste of the young earth. In the hot underworld, Water changes the crust it meets, serpentinizing peridotite, weaving hydrogen and oxygen into new minerals, storing some of itself as hydroxyl, while coaxing out gases that will return to the sea. When the warmed water finds a path back up, it bursts into the ocean as hydrothermal vents, black smokers, white smokers, shimmering seeps that look like ghosts exhaling. To the eye, they are plumes of dark fluid. To the ear, if the ocean could carry sound that far, they would be the planet's quiet sighs. Each plume is a letter from the mantle. Here is heat. Here are metals. Here is a little steam sent home. Ridges do more than decorate the seafloor. They help balance the books. As plates spread, some deep water returns to the surface, riding magmas and vent fluids. As those same plates age and stiffen, they drink again. Fractures admit seawater that hydrates the crust, priming it for the long descent it will one day make at a trench. Give the system time and you see the exchange. Exhale at the ridge, inhale at the trench. A planetary respiration measured in millions of years. Life listens too. Around the vents, whole communities build their days on chemical sunlight, bacteria feeding on the gifts of rock and heat, tube worms and clams opening and closing like slow flowers in the dark. Their world exists because the deep cycle never stops talking to the ocean, because water is both messenger and message in a conversation older than coral. Run your hand in imagination along a fresh basalt pillow. It is glassy, salt still drying on its skin. Inside, tiny bubbles tell you it carried gas, a breath from below that found its way into the sea we know. The hidden ocean has no shoreline, but at the ridges you can feel its pulse, steady and calm, as if the planet were asleep and dreaming of rain. Before there was a hidden ocean, there had to be water. Not lakes or rain, but the first molecules that would, in time, become cloud and river, mantle, memory, and sea. The origin story is quieter than a myth and more tangled than a shoreline. Some water likely arrived with the stones themselves. Primitive meteorites, carbonaceous chondrites, carry hydrated minerals and water-bearing organics. In the young solar system, dust and pebble-sized travelers drifted inward, delivering hydrogen and oxygen folded into rock. Other water may have come later, in gentle pelting from asteroids or comets after Earth's crust had cooled enough to keep what fell. Each impact was a note in a growing chord, not a deluge, but a long accumulation. Yet delivery is only half the tale. Early Earth was hot, molten in places, hammered by collisions, wrapped in a newborn atmosphere heavy with volcanic breath. Water dissolved into the mantle then, as it still does now, hiding in the lattices of minerals that could host it. When the surface cooled and a crust hardened, volcanoes became the translators, exhaling steam into skies that could finally hold clouds. Rain fell, and the first oceans gathered in basins sculpted by gravity and time. From the beginning, then, water was both traveler and resident, part of rock and apart from it, slipping between roles as the planet set its rhythms. That dual citizenship matters. If all water had stayed at the surface, Tectonics might have stalled. If all had sunk, the sky would have been bare. Instead, Earth became a dialogue, subduction tucking moisture into stone, volcanism sending it back. The hidden ocean grew not as a place but as a capacity, rooms inside minerals opened by pressure that could keep water safe for an age and return it when the world was ready. There is comfort in this origin. It says that habitability isn't only waves under stars. It's also hydroxyl in the dark, stored patience that lets continents glide and climates find their balance. Our oceans glitter because the mantle remembers. Close your eyes and picture the first rain. The drops were ancient travelers finally learning the word home. Some stayed to carve rivers. Some slipped under a ridge and began a long descent, a promise that one day, far in the future, steam would rise again to meet the moon. To understand a sea that hides inside stone, we build suns and mountains in rooms no larger than a closet. In high-pressure labs, geologists coax minerals into their deep earth shapes, then ask them what they can carry: heat, sound, electricity, and most importantly tonight, water. One tool is a multi-anvil press. Steel frames, tungsten carbide anvils, and a tiny cube at the center where a sample sits like a secret. Another is the diamond anvil cell, two flawless tips of diamond squeezing a grain of mineral smaller than a poppy seed. Wrap it with a heater, let it glow till it is a small star, and you have, for a moment, the pressure and temperature of the mantle's twilight. Into that star we place the familiar ingredients of the upper mantle, olevine's chemistry, then press until the lattice must choose a deeper identity. First wadsleyite, then ringwoodite. We let a whisper of water join the mix, not as liquid, but as stray hydrogen that can hook into the crystal pattern. Later, when the pressure is eased and the sample is freed, we read its memory. Reading happens in many dialects. Infrared light reveals the fingerprints of hydroxyl. Raman and Brillouin scattering tell how stiff the crystal is, how fast a seismic wave would run through it if it lived at depth. Tiny needles of electrons map the elements. Sims counts isotopes one by one. If the crystal carried water, these methods catch its shadow, bands and shifts, peaks and whispers where there would otherwise be quiet. The answers repeat, gently, across labs and techniques. Wadsleyite and ringwoodite can host surprising amounts of water in their atomic rooms. A trace of that water softens the mineral, lowers melting points, brightens electrical pathways. Change the temperature and the capacity changes. Change the pressure and the lattice rearranges again, tightening or opening the rooms where hydrogen can rest. In this way, benchtop stars sketch the boundaries of a hidden ocean. There is humility in these experiments. The samples are specks, the timescales minutes or hours, the pressures borrowed, the heat artificial. And yet, when their results meet the planet's own signals, seismic kinks at 410 and 660, conductive patches that glow to radio waves, a diamond's blue-gray fleck of ringwoodite, the stories fit together. Lab and Earth nod to each other like old friends who grew up in different towns but remember the same river. If you listen closely, you can hear the romance beneath the rigor. Humans building tiny universes to ask a stone if it knows how to drink. The stone answers in spectra and moduli, and we translate those answers into weather forecasts for a place no eye will ever see. Wetter here, drier there, softer here, stiffer there, more likely to melt when a plume passes through. Hold that picture as we climb from the lab back into the field, not to the ocean this time, but to the oldest, thickest roots of continents. Some of Earth's most ancient foundations seem almost deliberately dry, yet even they bear whispers of deep water's touch. Beneath some of the calmest landscapes on Earth, the planet keeps its oldest bones. Geologists call them cratons, ancient continental hearts that have held their shape for billions of years. Under each, a keel of mantle rock extends deep like the root of an old tree. It is cool, light, and most of all, dry. That dryness is not a footnote. It is the reason these roots endure. Without much water in their minerals, the rocks are stronger and more resistant to flow, as if the hinges of the deep had been tightened long ago and never oiled again. Hold a piece of that keel in your mind. It is depleted peridotite, harzburgite and lurzelite that long ago gave up melt to build the continents above. In losing melt, it lost water too, growing buoyant and stiff. Dry stone resists. Dry stone remembers its shape. That is why the cratons don't wander like new crust does. They glide as one piece, a raft with a thick, ancient keel. And yet, even here, water finds a way to write soft margins on a hard story. Kimberlite eruptions, those fast elevators that bring diamonds to daylight, also carry slivers of the keel itself. Xenoliths chipped from the root and flung upward. In them we see veins and pockets where later fluids passed through. Thin seams of phlogopite mica, traces of amphibole, whispers of carbonate. These are the signatures of metasomatism, a gentle reworking by melts and fluids that arrived long after the keel first formed. Where did those visitors come from? Sometimes from above, as subducted slabs slid beneath the continent and exhaled residual water into the base of the keel. Sometimes from below, as small, volatile, rich melts rose from deeper mantle or from plumes that had paused to sip the transition zone's stored moisture. The keel stays mostly dry, but along its cracks and old scars, the hidden ocean breathes through intermediaries. Tiny films of melt, pockets of gas, ions drifting like rumors through crystal. Even a trace changes the mood. A smear of water-bearing mica along a grain boundary can soften a patch the size of a city, turning a locked hinge into a quieter one. A breath of CO2 and H2O can lower the melting point, just enough to start a trickle of carbonated melt, the kind that can carry diamonds and metals and one day erupt as a kimberlite. The keel is not saturated. It is stippled, dry background, wet punctuation. Seismology sometimes catches the accents. A slightly slower corridor under an ancient shield, a zone that conducts electricity a touch more willingly, a boundary where stiff gives way to supple for a few kilometers. In hand samples, the story becomes tactile, a vein like a healed lightning bolt, a mica flake glinting where only olivine should be. The deep roots keep their dignity, but they are not sealed against whispers. If the transition zone is Earth's water memory, the cratonic keel is its archive of continuity, a long chapter heavily underlined, with margin notes added in a finer hand by passing fluids. Stability does not mean silence. It means a music so steady you only notice it when a soft instrument joins for a bar and then slips away. Even the oldest stones have futures. Sometimes a continent that has slept for an age turns on its side and sighs. The sigh begins invisibly, heat gathering under a thick keel, drips of soft asthenosphere rising toward a roof that has grown thin at the edges. A rift is not a sudden tear. It is a long exhale. The land stretches by millimeters, then by more. Valleys lengthen, faults step like staircases across a plain, and secret fires begin to stitch light into the dark. At depth, water has a hand on the dimmer switch. Along the base of old keels where earlier fluids once left faint seams of mica and carbonate, the rock is a shade more willing to yield. A little water in grain boundaries, a little in the lattice, and the hinge creaks open. As the lithosphere thins, the asthenosphere rises and decompresses. Water lowers the temperature at which the first bright beads of melt appear, so magmas are born earlier, at smaller degrees of melting, rich in volatiles and stories. Those magmas carry accents from their birthplace. Some are alkaline, dark and glossy, climbing through old scars and lighting them briefly like constellations rediscovered. Some are carbonated, whispers from the deep that can flow like ink and leave behind minerals that glint under a hand lens. In places, the melt never reaches the sky. It cools into dikes and sills, quiet signatures you can only read when erosion opens the page. In others, it builds cones and cones again, each eruption another line break in a poem about a continent learning how to breathe. Seen from far above, rifts make necklaces, chains of lakes and volcanoes, linear valleys that catch morning fog. Seen from within, they are rooms where the deep cycle meets the surface in patient increments. Fumaroles that bead with moisture, hot springs that taste of stone, basalt pillows that steam in the first rain. The hidden ocean does not arrive as a flood. It appears as influence, hydrogen bound in minerals that made melting easier when the land decided to drift. Rifts have memories and intentions. They follow old sutures where ancient continents were once stitched together. They widen over lifetimes and then, sometimes, stop, leaving only a scar that later rivers will learn to trace. Or they keep going until a thin place becomes a newborn ocean with edges still warm to the touch. Along the way, water's soft hands keep time, easing flow, priming melt, giving the rising gases something to say when, at last, they reach the wind. If you walk a rift at dusk, you might hear it, a faint, far murmur like waves in another room. That is the future ocean, practicing its voice. And underneath, in the dark, the hidden ocean is practicing too, trading small favors with heat so the surface can one day learn a new shoreline. For most of the mantle, the 660-kilometer boundary feels like a shoreline. Above it, minerals with tiny rooms welcome hydrogen. Below it, the rooms close and the stone prefers to travel light. And yet, along the cold spine of a sinking slab, water sometimes finds a passport. In chill conditions, special minerals appear. Dense hydrous magnesium silicates, the quiet specialists' geologists' nickname DHMS. They go by modest code names in the lab: Phase A, superhydrous Phase B, Phase D. But their work is clear. They bind water tightly enough to survive pressures that would wring other hosts dry. Think of them as sealed canteens tucked into the luggage of a descending plate. As the slab kneels through the transition zone, many hydrous minerals give up their cargo. Amphiboles first, serpentines later, exhaling water into the mantle wedge above. But deeper in the slab's cold core, DHMS can persist. They slip across the 660-kilometer gate and carry traces of water into the lower mantle, past the point where ringwoodite yields to bridgemanite and ferropericlase. Not much makes the crossing, just whispers compared with the twilight reservoir above, but enough to matter where rock is very strong and change is slow. Eventually, even these couriers tire. Warmth increases, the slab bends or breaks, and the phases transform, releasing water into a country that rarely sees it. Down there, a breath of H2O is leverage. It can lower melting temperatures along shear zones, soften the edges of deformation, and seed tiny pockets of melt that change how heat and motion move. Some of that influence may ride upward with sluggish currents. Some may wait eons until a plume arrives to lift it toward a future sky. The image is delicate, a ribbon of winter threaded into summer, carrying sealed notes through a checkpoint most travelers cannot pass. Each note is small, but the route is long, and over geologic time, even small deliveries shape the ledger. They remind us that Earth is not a set of boxes stacked in tidy layers. It is a conversation between layers, with cold slabs and warm plumes trading messages in elements and phase changes. If you press your ear to this story, you can almost hear the footfall, the crisp step of a courier on stone stairs, the soft tear of an envelope opening far below. Inside, only a few words: hydrogen, oxygen, but in the right place they can tilt the balance of a planet. When rock melts, it keeps a diary. The handwriting is chemical, ratios, traces, tiny asymmetries in isotopes. And within that script, water leaves its mark. You cannot see it in a glowing fountain of lava, but when the rock cools to black glass and the glass is ground and red, the story appears. Start with water itself. Basalts from the seafloor, born at mid-ocean ridges, carry modest amounts of H2O, often a few tenths of a % by weight. Hotspot lavas, raised by plumes that may sip the transition zone, can be richer. Their glasses hold more dissolved water. Their crystals grow differently because of it. Their bubbles tell of gas that wanted out. The difference is quiet but consistent, like a regional accent. Then listen to hydrogen's twin identities. Some atoms are slightly heavier, deuterium instead of common hydrogen. The ratio between them, the DD signature, is a compass. Seawater and recycled sediments lean one way, the drier upper mantle another. When a lava carries DD that echoes the ocean, it hints that its source once breathed air and rain, long ago subducted, stored as hydroxyl in minerals, then melted and risen to speak again. Other volatiles, chlorine, fluorine, sulfur, add margins to the note, tracing whether the melt tasted sediments, altered crust, or the cleaner mantle beneath. Even noble gases, so aloof they scarcely react, join the chorus. Helium comes in flavors, ancient three. He from the planet's formation, and four. He grown by radioactive decay. Some plumes arrive with higher 3He or He, like a breath from reservoirs that have slept deep and long. When such lavas also carry generous water, the pairing feels like a memory. Heat from below meeting moisture remembered in the transition zone above. Geochemistry is patient work. A chip from a flow is melted or dissolved. Instruments count atoms by the millions. Plots bloom like constellations on a screen. The constellations repeat across islands and arcs and ridges. Mid-ocean ridge basalts draw a steady baseline. Arc lavas lean toward the sea, rich in volatiles, spiced with the chemistry of subducted life and mud. Ocean island basalts scatter wider, some whispering of deep time, some of recycled rain. None alone proves a hidden ocean. Together, they sketch its shoreline of influence. There is a tenderness in realizing that a raindrop can become a number on a graph millions of years later. That number lives in a stone you can hold. It says, I fell, I flowed, I sank. I learned to speak as hydroxyl. I waited in the dark. I was lifted by heat. I lit the night for a moment. I cooled. I was red. The circle closes not with spectacle, but with understanding, a kind of light that does not need flame. Next, let's turn the page from fire to time and ask how fast the deep water cycle moves. How long does a molecule spend as mineral memory, and what sets the tempo of this slow breath? Every cycle has a beat. Rain and rivers keep a quick rhythm, hours, days, seasons. The mantle's water cycle moves to a metronome you can barely hear. It begins fast enough. Seawater slips into hot new crust in years, decades at most, stitching itself into minerals along fractures and pillow rims. Then the tempo stretches. The plate cools, grows heavy, and drifts for tens of millions of years before kneeling at a trench. What was weather becomes geology. Descent is not a plunge so much as a long lean into darkness. Along the way, hydrous minerals unfasten in stages, releasing water upward to help right arcs of volcanoes. But some of that cargo rides deeper, folded into tougher hosts that can tolerate pressure. In the transition zone, hydrogen finds rooms in wadsleyite and ringwoodite, and time opens still wider. A molecule can linger there for ages, waiting on the slow choreography of convection, on a slab that stalls or a plume that arrives like a warm invitation. How long is ages? There isn't a single number. There's a distribution. Some parcels of rock in the transition zone may turn over in a few tens of millions of years if circulation is lively. Others may sit much longer, especially where cold slabs pool or where flow patterns loop instead of cross. The planet's interior is not a conveyor belt, but a braided river, channels that split and meet again, with eddies that keep their contents drowsy and still. The return journey can feel sudden only at the end. A rising plume that sips stored water crosses thresholds where melting begins, and once melt appears, buoyancy helps. Magma ascends, gases exsolve, and what slept as hydroxyl in crystal becomes a cloud over a moonlit ridge. Yet even those sudden acts are prepared by slow decades of ascent, centuries of cooling, millennia of building a shield or a cone, quiet work stacked into a visible moment. There are pulses in the record, long floods of lava that mark chapters when the deep exhale quickened, quiet intervals when the ledger favored storage over release. Surface climate feels these only in the longest averages, as background adjustments to how much fresh basalt is fed to rain, how strongly weathering draws carbon from air, how often volcanoes send steam and ash skyward. A faster verse here, a slower verse there. The poem holds. If you need an image, think of two metronomes on the same table. One ticks quickly, clouds, storms, rivers. The other swings so slowly you forget it's moving. Plates, plumes, minerals that learn to drink. Touch the table and both adjust, tiny exchanges passing through the wood. That's Earth, the shallow cycle and the deep cycle sharing a surface, nudging each other in ways that only make sense when you listen a very long time. Some planets wear armor that never bends. They keep a single, unbroken shell, no drifting continents, no trenches kneeling into the deep, only scars from impacts and a long, silent cooling. We call that a stagnant lid. Earth is different. Its surface is a mosaic of plates that meet, part, and pass. The difference is not just size or chance. It is also water, at the surface, yes, but more quietly in the mantle, where a trace of hydrogen threaded into crystal can change how a world decides to move. On Venus, heat rises from within, but the lid holds. The crust is young in places, catastrophically resurfaced, yet we see no persistent subduction, no global conveyor of plates. Part of the reason may be dryness. Without much water in the rocks, grain boundaries are tighter, defects stingier, the asthenosphere less willing to flow. The hinges of the planet remain unoiled. Add extreme surface temperatures and a dense atmosphere, And you have a world that vents heat in sporadic sweeps rather than through quiet, continuous plate dance. Mars tells a different cautionary tale. Smaller, it cooled faster. Whatever water it once folded into its mantle and crust was limited and lost more easily to space. With less internal heat and a drier, thicker lithosphere, the planet stiffened early. Volcanic giants, Olympus Mons and its kin, rose from stationary plumes beneath a lid that never broke into plates. The music is there, but the instrument stayed braced. Earth's secret is softness in the right places. Not mush, not melt everywhere. Just enough water in the mantle's fabrics to lower friction, to ease diffusion, to reduce the temperature where the first bright beads of melt appear. That softness keeps the asthenosphere supple, a pillow sliding under the lithosphere. It helps faults creep until they must slip. It helps slabs bend rather than shatter. It helps plumes rise and, when they meet stored moisture in the transition zone, begin to melt with a little more eagerness. The result is not chaos, but choreography. This matters for habitability in ways that feel personal. Moving plates build mountains that weather to feed rivers that feed seas. They recycle nutrients, balance carbon over long spans, and stitch fresh crust where life can find chemical energy at ridges and arcs. The deep water cycle, rain to trench to hydroxyl to steam, acts as the planet's metronome, keeping the tempo of this exchange steady enough for oceans to persist and climates to recover from their own experiments. Hold the triad in your mind. Venus, too hot and likely too dry inside to loosen its lid. Mars, too small and too dry to keep the dance going. Earth, just wet enough in the mantle to oil its hinges. Just active enough to keep the poem of continents moving without tearing the page. Our hidden ocean does not glimmer, but it keeps time. It is the quiet reason mountains wander and shorelines redraw themselves like handwriting practiced over ages. Some nights, when the house is still, you can feel a similar kindness in your own body. A little water where joints need it. A breath that lets something stiff become willing. Earth carries that willingness in stone. When we look up and wonder which distant planet might breathe, we often picture shining seas. But habitability isn't only water on the surface, it's also water within. Whispers of hydrogen tucked into stone, oiling the hinges of a world so its skin can move, recycle, and heal. The hidden ocean beneath our feet becomes a lantern we can carry to other skies. Imagine a super-Earth, larger, heavier, its mantle squeezed tighter than ours. Under such pressure, minerals with tiny rooms for hydrogen may hold even more water than here, at least in some layers. That interior moisture could keep the asthenosphere supple, helping plates glide instead of lock. A planet that can regas, pull water down at trenches, and dega, send it back through volcanoes, has a way to balance its climate over deep time, the kind of patience life needs. Now imagine the opposite. A dry mantle. Without water threaded into the lattice, rocks grow stern. Grain boundaries seize, melting begins later, and the lid hardens. Heat still tries to rise, but instead of quiet plate dance, you get spasms, rare global resurfacing or long stagnation. Oceans, if they exist, may come and go without a partner below to steady them. The sky writes quick poems. The stone refuses to rhyme. There's a third picture, the water world, with an ocean hundreds of kilometers deep and high-pressure ice phases sealing the seafloor. Abundant surface water sounds friendly, yet if ice blocks the exchange with rock, the deep cycle can't turn. Nutrients may starve, carbon may drift out of balance, and the thermostat loses its long corrective breath. In that quiet, the hidden ocean we've come to love, water and minerals, traded by plates and plumes, matters even more as a concept. It reminds us that habitability is choreography, not inventory. These are not just armchair guesses. Telescopes measure starlight filtered through alien skies, hinting at steam and clouds. Models test how pressure reshapes minerals, how much water a mantle could keep, whether plate tectonics can start and survive. The answers are early and imperfect, but they lean toward a Goldilocks inside. Not too wet at the surface to seal the crust, not too dry in the mantle to lock the hinges. A world where the shallow and deep cycles share a table and pass the bread. Hold Earth in your palm for scale. Our deep water cycle does not sparkle, yet it keeps continents wandering, volcanoes breathing, and climates recovering from their own experiments. If we ever read the weather of a distant shore and sense the same slow metronome, rain to trench to crystal to cloud, it will feel like meeting family. Some nights, I like to think the universe practices this song in many keys. On some worlds, the tempo is faster, on others, slower. But wherever stone remembers water and returns it with patience, time may gather enough quiet to make room for listening hearts. In the dark where ridges breathe, water meets bare mantle and something generous happens. Hot rock rich in olivine drinks seawater and changes. Minerals rearrange, new crystals grow, and simple molecules are set free. Among them is hydrogen, a tiny fuel with a patient flame. This quiet chemistry has a name, serpentinization, but the feeling of it is simpler, stone and water eking energy together. Follow that energy to a place like the Lost City hydrothermal field, where warm, alkaline fluids rise through the seafloor and build pale chimneys that look like coral carved from moonlight. There is no sunlight here. Only gradients, differences in temperature, acidity, and chemistry that living things can harvest. Microbes perch on the edges of those gradients and go to work, stitching carbon into organics using hydrogen as a handle. Later, larger creatures gather, worms, snails, crustaceans, each a small lantern lit by chemistry instead of day. Why tell this story in a tale about a hidden ocean? Because the deep water cycle sets the stage. Without water circulating through new crust, there is no serpentinization. Without a steady exhale of heat at ridges, there is no vent flow. The same planet that tucks rain into minerals and keeps it sleeping for ages also arranges, at the surface of the deep, these little factories where rock, water, and heat write recipes for life. Some scientists think life may have started at vents like these, within the thin, maze-like walls of mineral chimneys. Those walls create microchambers, each a pocket where ions sort themselves and gentle voltages arise. In that sheltered geometry, carbon can be coaxed into more elaborate forms. You don't have to choose that origin to feel the grace of the idea, that a world with moving plates and a remembering mantle offers not just scenery, but opportunity, countless chances for simple chemistry to climb toward complexity. Even today, when continents wear forests and the sky glows with weather, vent communities remind us of the foundation. They thrive on rock-borne gifts, hydrogen, methane, metals, and warmth. When a plume, far below, sips moisture from the transition zone and later helps build new seafloor, it is, indirectly, feeding these quiet cities. When subduction drinks ocean water and returns it to the deep, it is renewing the ingredients list for reactions that turn geology into metabolism. Hold that connection gently. A raindrop that once cooled a mountainside becomes part of a mineral, rides a plate, sleeps as hydroxyl, rises as steam, falls again to the sea, sinks into new crust, and helps free the hydrogen that lights a microbe's world. The loop is enormous, but the joy is local. A single cell dividing in the dark because stone and water keep their promises. In the next part, we'll come back toward land and listen to mountains, their making, their weathering, and the way deep water quietly decides how stiffly they stand and how softly they fall. Mountains feel solid beneath our boots, but they are born from motions as patient as breathing. Deep below a rising range, water is already at work, quiet, precise, helping rock decide whether to hold fast or yield. At convergent margins, a sinking plate exhales water into the warm mantle above. That water lowers the temperature where melting begins, feeding arcs of volcanoes that stitch fresh rock onto continents. Far inland, where continents collide, water plays a subtler role. A trace in the lower crust weakens grain boundaries, invites minerals to recrystallize, and turns stubborn rock into something willing to flow. Deformation localizes along hydrated shear zones. The crust thickens and shortens. A mountain belt gathers height the way snow gathers on a quiet fence. Metamorphism is the mountain's private weather. Fluids thread through fractures and foliation, carrying heat and elements, painting thin quartz veins like lightning frozen in stone. Blue-schist forms in the cool, high-pressure corridors of subduction. Eclogite follows deeper, where basalt is remade tougher. Serpentine blooms in the mantle wedge where peridotite meets water. A mineral with the color of old forests and the strength to change how faults slip. Even earthquakes answer to fluids. At depth, a breath of water lowers friction and turns some snaps into slow, shivering tremor. Then the sky arrives. As peaks rise, they teach the wind to rain. Moist air climbs, cools, and lets go. Clouds brush the ridge lines and spill their silver. Water falls as snow and storm, carves gullies with glacial patience and riverine insistence, and mixes with carbon dioxide to make a weak acid that nibbles at feldspar and olivine grain by grain. Chemical weathering draws carbon from the air and tucks it into clays and oceans. Physical weathering breaks cliffs into talus, talus into sand. The mountain exhales into the sea in 1,000 small streams. This is the long duet. Water in the deep makes mountains possible by softening stone where it needs to flow. Water at the surface makes mountains mortal by teaching rock how to fall. Erosion lifts as it lowers. Strip weight from a range and the crust rebounds, inviting new rock from depth to take the cold. The belt breathes. Uplift, weathering, isostatic rise, weathering again. Sediments raft the mountain's memory to deltas. Subduction tucks some of that memory back into the planet, where fluids will one day write another range. Touch a ridge at dusk and you can feel both partners. Underfoot, a continent that rose because hydrogen found rooms in crystal thousands of meters below. On your cheek, a wind heavy with mist that will, grain by grain, return this height to the sea. Between them is time and the hidden ocean, keeping the ledger with a steady hand. Even now, after diamonds with secrets and wave maps humming with hints, our picture of the hidden ocean is only a lantern's circle on a wide floor. The rest is shadow, not because the story is false, but because it is still being written. We don't yet know how patchy the reservoir truly is, whether the transition zone is a gentle drizzle everywhere or a mosaic of downpours and droughts. Some tomorrows seismologists will sharpen their images until they can see wetter corridors braided between drier buttresses, like veins of night running through dusk. Other tomorrows, new lab measurements will teach us how much water minerals can carry when iron rises or temperature falls by the smallest degree. How a trace of nickel, a shift in redox, a breath of carbon changes what hydrogen is allowed to be. We don't yet know the turnover time, the tempo of the deep breath. Does a raindrop that becomes hydroxyl in ringwoodite wait 50 million years or 500 before a plume invites it back to the sky? Is the ledger steady across eras, or does it swing, ages of storage followed by ages of release, tilting the background climate in ways we only feel when we count fossils and ice? We don't yet know how far couriers can carry their notes. Cold slabs sometimes thread the 660-kilometer gate, sealed minerals guarding their water into the lower mantle. But how much of that whisper survives? And where does it matter most? In shear zones that cut the deep like quiet ravines, in slow eddies where heat is patient and motion polite. Each possibility is a door. Behind each door, a new way for water to edit the planet's script. We don't yet know the full conversation with life. Hydrothermal chimneys breathe because ridges exhale and plates inhale. Mountains rise because deep water softens stone where it must yield. But how tightly are these moments braided to the fate of climates, reefs, forests? If the deep cycle hums a little higher or lower, How does the surface poem change its rhyme? And yet, this uncertainty is not a void, it's an invitation. Every instrument we invent, every spectrum we read, every quake we translate pushes the lantern's circle a little wider. What we see already is enough to change how the world feels underfoot. Stone as an archive, water as a strategist, climate as a duet between sky and mantle. Enough to sleep easier knowing that even in darkness, the planet keeps a careful ledger, returning what it borrows in time. Set the map on your lap for now. Let the edges be soft. Tomorrow will sharpen some lines and blur others, as good maps always do. Tonight, it's enough to know that beneath mountains and cities, a quiet ocean of possibility is held in crystal, patient as breath. Set your palm on the ground for a moment. Floorboard, soil, the cool flank of a river stone, and imagine the quiet beneath it. Not silence, but a layered hush. Plates kneeling, plumes rising, crystals turning in their sleep. In that hush, water is everywhere and nowhere at once. It steams at ridges, whispers through faults, and, most of all, waits as hydroxyl in the lattices of minerals that never see the sun. That waiting is the hidden ocean, not a place with shores, but a capacity that the planet fills and empties in its own long time. We have walked its borders together, through the twilight of the transition zone where olivine becomes wadsleyite, then ringwoodite, and tiny rooms open for hydrogen to rest. We listened to earthquakes that shouldn't exist, and learned how cold slabs and phase changes make room for a rupture even in warm depths. We met couriers, DHMS phases, that carry sealed sips of water through the 660-kilometer gate, and we watched plumes pause to drink from the reservoir before writing islands on the sea. We read chemical diaries in lavas, held a diamond that brought a blue-gray fleck of ringwoodite from 500,000 kilometers down, and traced electric whispers that sketched wetter corridors no eye can see. On the surface, that deep patience becomes weather and memory. Volcanic steam rejoins clouds. Mountains lifted by fire are softened by rain. Vents at night feed cities of life that glow without sunlight. Over eras, the hidden ocean keeps the hinges of the world oiled just enough for continents to drift, seas to cycle, and climates to find their balance again after wandering. Even our search for other worlds carries this lesson. Habitability is not only lakes under stars. It is also a mantle willing to move because stone remembers water. If the story feels soothing, it's because its tempo is human scale in the ways that matter. You and I will never see a slab cross the transition zone, but we know the feeling of breath that steadies a body, of joints that move more kindly with a little water. Earth carries that kindness in crystal. The ledger is careful. What falls as rain may one day travel as lattice, then rise as steam, then fall again as rain. Nothing is lost. It is only translated. So let tonight end where it began, with the sense that the ground beneath you is not merely support, but conversation. The planet is speaking softly, keeping time in hydrogen and oxygen, turning darkness into the conditions for light. You can rest inside that rhythm, the slow inhale of stone, the quiet exhale of rain, and wake knowing the poem continues whether or not we watch it.